Hello and welcome to the class Learning AI, our first week program in the class Applied AI. This week today we will look at the Perceptron model. The Perceptron is an artificial neural network that was invented and developed by Frank Rosenblatt in 1957. And you may wonder, why are we looking at a 60-year-old neural network instead of using or just applying some of the contemporary deep neural networks? And the reason is that this first week is really about learning and understanding how these artificial neural networks work. And the Perceptron model is really a good entry point into understanding the mechanisms in neural networks and especially the mathematics. It is, on the one hand, it is a classical model of supervised learning where you have labeled data and you can compute an error signal based on what the network predicted as outcome and what your labeled data says. You can look at the function of the basic unit in artificial neuron and look at the mathematics there, and these mathematics are basically the same as the mathematics computed in a deep neural network. And in the same time, we can sidestep some of the problems that you face when you look at deep neural networks, and the biggest issue to tackle is to understand backpropagation learning. We don't have to deal with this so far, but yet you can get an intuition of what the problem is, of why backpropagation algorithm is needed based on this model. So the Perceptron model by itself is a relatively simple structure. You assume that you have some sort of input layer with input nodes that can be understood as sensor elements. In the original machine, the Perceptron machine, these were really light sensitive elements. For now, we assume that these input layers take some numerical value of between 0 and 1, and this input layer connects to an output layer. The number of nodes of the output layer corresponds to the number of different labels that you have. So if we imagine we had a Perceptron network that would be able to recognize an A, a B, and a C, these three nodes would stand for the A, the B, and the C. And in case the network could also recognize a D, we would have to add another node. In the Perceptron model, we have a densely connected network. That means that every node in the input layer connects to a node in the output layer. So this is how the network looks. This is the output layer. And in between we have what is called the weights. The weights determine how strong a node affects through a node from the input layer affects a node in the output layer. So this is a basic setup we will be looking at this morning. And I will step you through the computation needed, on the one hand in a forward way of how to compute what arrives at the output layer, or how the output layer responds given some input pattern at the input layer. And to do so, we consider a very basic example. We first consider the logic OR. And again, you may wonder, why are we looking at such an academic, non-applied example? Because it's most probably something you will never use in your network to learn the R. There are two reasons. One is it's an historical reason, and that was that initially one of the first proposals for developing artificial neural networks is even from an earlier time, from the late 40s, by McCulloch and Pitts, who had shown that in theory you could construct any logical function using a neural network. And based on this insight that you could do all logics a computer could do with a neural network, eventually makes you understand why the excitement at that time about neural networks. And it's also part of the story on neural networks that at some point Marvin Minsky could show that the Perceptron model could not learn the XOR, so the exclusive OR, which resulted in a stop of neural network research for something like 15 years. So it has, that's one thing. The other thing is what we do this morning, I will step you through some handcrafted code using standard JavaScript arrays on computing and on computing an artificial neural network that produces a logic OR, and in a second step, that's the second lecture on how to realize a program that, or an artificial neural network that learns the logic OR. As exercises, you will be looking at the logic AND. And what is interesting about this is in the afternoon, we will re-implement the whole thing using the TensorFlow software library. And then you will see it's quite easy to extend once you have constructed the network that learns the OR and the AND. It is quite easy to expand that network by just changing the input vectors basically and the output vectors to do something like handwritten digit recognition on the MNIST dataset. So that's sort of the plan, and that's why we first look at the logic OR. I've put in the script, I've put an example that I think you should all be familiar with from your coding practice. It's this expression here where we combine two expressions. So the first one checks whether the mouse in the X direction is smaller than 100. And we combine this expression with checking the mouse Y. So in Y direction, the mouse position, and if in mouse Y, we are larger than 100, and these two expressions are combined into an OR statement. So if one of them is true, or if both of them are true, the program will execute the following statements. And the truth table for the logic OR is, so we have the first expression x1, second expression x2, and the result y. The truth table is constructed by going through all possible combinations of these two expressions. So they can both be false. In our example, that would be if the mouse X position is larger 100 and the mouse Y position is smaller 100, then the logic OR also returns a false. If one of the conditions is met, then the logic OR is true as well. And if both are true, the logic OR is true as well. And here that's in common language. When you would, if you ask someone you want tea or coffee, the OR which we are using is actually the exclusive OR, which is an either or question. Whereas the logic OR, this is the truth table to work with. And what we want to do now is we want to construct an artificial neural network that computes the truth table. So it's one step before learning. It's just setting up a network so that it computes the OR. And in a second step, we will look at how the learning goes. And to translate this truth table or the OR function into an artificial neural network, we have to we are using some simplifying assumptions. To simplifying assumptions not about the mathematics here, but simplifying assumptions of what a neuron is. I've included below here two examples of neurons in organisms. The first one is to show you that there is a large structural variety of neurons. So neurons can have very different forms, and connected to these different forms are also different functions. So they don't operate all the same. And the second example shows you kind of like the chemistry which is happening at the synapse of a neuron. And this is to give you an idea of the complexity of the very process of a neuron switching or becoming active. What we assume is that the neuron is actually a mathematical in our abstraction. We think of the neuron as something that sums up incoming connections. So these incoming connections could be from another network, input from another network, or from some sensor or whatever. And what happens at this level here is that the neuron is summing up all these incoming signals. Incoming signals means that, for example, here actually we feed in some number, again something for now for the logic OR we can assume that it's either 0 or 1, so we can just take Boolean values here. If a neuron is active, we could simply fill it with color, so that would be an active neuron, this would be inactive. And this activity would be a value of 1. If it's inactive, it's a value of 0. And this activity is passed through a weight, which is again a rational number between, it can be negative, positive. There is actually no limitation on these weights so far. And so we assume we have here our input node x0, weight w0, input node x1, input node x2, weight x1, weight 1 and weight 2. And the mathematical operation we are now doing to compute the incoming activity into this neuron is primary school mathematics, multiplication and addition. What we do is we take the value of x0, we multiply it with w0, we add x1 times w1, and we add the third term x2 times w2. So this is basically what's happening at this stage of the neuron. And then there comes another important stage, and that is what is called the threshold function. That is to stick with the biological image of a neuron. That would be this idea of a neuron that when it's stimulated enough, so when there is enough input, the neuron starts to fire or output a burst of activation. And this is here approximated with the threshold function. The threshold function is, so basically you look at this axis here and you have our sum is either some value here, around here. If we assume this would be 0 for now, then that would be for some negative value. The output of the threshold function is 0, and if we are on the right hand side, so if we are here, then the output of the threshold function would be 1. And that brings in one additional parameter which is important, that is called the bias term. The bias term is actually a term that is used to shift around where that threshold function will switch. You can imagine it could, instead of being at 0, it could as well be at a value of 3 or wherever on that x-axis it could be positioned, and that's one of the parameters that is usually learned within the learning of artificial neural networks. This bias term is actually when you, so the threshold function itself, if we call that t of x, is defined as follows. For x smaller or equal to 0, it gives 0 as result, and for x larger 0, it gives 1 as result. And now if you think of the whole expression, so if we look at what we have as output here of this neuron, then y would be basically the threshold function of this sum plus the bias term. Okay, that is the complete mathematical expression. And now, because this bias term is something we want the network to learn, some people came up with a trick, a mathematical simplification, replacing basically this model with a model where the bias is actually turned into a weight. And this is done by adding one additional input. So before we had 3 neurons, and the first input is always set to 1. And all our nodes connect to the output node of our neuron, where we do the summation. This would be now x1, x2, x3, and this is x0. And if this one is set to 1, basically the bias term is now encoded in the first weight, in W0, because this is always 1. We always have, as part of the sum, we always have 1 times W0, which is actually, if I bring back this equation here, where we have the sum plus the bias, so it's this term here that now appears as part of our summation here. And whether you call the bias or whether you call it W0 doesn't make a big difference. And this one is added then plus x1 times W1 plus x2 times W2 plus x3 times W3. and on the while we have a little bit more complication here because we have this additional term, here we only have a threshold function that switches at 0. So that makes the whole construction a bit easier. I've prepared the code for this in this example here, where I start this example. It basically produces the truth table as a visualization to check that our result is the right one. But you can play around with it and test out different configurations. So I take you through the code. What you see, the first array here is an array that holds all possible combination of our input values. So basically it constructs the truth table. So the first combination is this one where x1 and x2 are 0. When they are red, we assume a value of 1. The first term does not is not visualized. This is actually the bias term. That's the way that is always 1. You see here in every combination there is this term is 1, and then comes x1 and x2. So this is our input vector, the output vector is computed, and then something important here is the weight vector. This is basically, so actually the network we are considering is simpler than the one I did draw here. We don't have this x3 term. So we just have the bias term and then x1 and x2, right? If you look into the code you have here, basically this is for constructing these ellipses, and then here we compute the output of the neuron. And here you should recognize this is basically, this here is this expression, and then this expression is passed through a function called threshold, and this function you find here. It's basically, it checks if the input variable is larger 0, it returns 1, and for all other cases it returns 0. So that is the threshold function as I just had defined it here, basically. There's one thing, if you can play around with the script a little bit. One thing is that the solution here with the weight of 0, 1 and 1 is one possible solution. It's kind of like, it's relatively straightforward to come up with this weight setting if you given the result we want to obtain. This is one thing I would recommend you to do on your own, to once do that computation for these different values of x1 and x2, and you will see that you get the right truth table. But it's not the only combination where you get this this truth table. It's also we get the same result if we put something here like minus 2.5 and let run the script. We get the very same result. So there is a range of weights that produces this same result. And the first exercise for playing around with this script is to find a weight combination that produces as output the end function. So it's basically modify the weight vector in order to produce an output that looks like the end function. I hope you remember the end function. It would be, I quickly draw the truth table, how it should look. And now I use this notation of circles. So if they are on when they are black, okay, and the end function only, the result only goes on when both are on. This is the logical end. So that's kind of like your task. You can do that either by just fiddling around with these values, that's fine for me, or you can try to do it in a more analytical way and think about what kind of weight combinations given the function that is really computed, and this is this function here. So what you do is you multiply 1, this is always 1, with the first entry in the weight vector. Then you take the second variable, the expression x1, and multiply that with the second entry in the weight vector, and then you take the expression x2 and multiply that with the weight vector, and then you get an output. Okay, that's it. No, there's one last. There's another exercise I want to quickly explain. What I would like you to do is you should expand. So the network which is realized here is a network with one output node, and here this is the bias term, and this is x1 and x2. And the function is right now, as you see it, is the OR. The first exercise is to modify the weights so that this becomes an end function. And then there's one other exercise is I want you to come up with a network that has two output nodes, and one we call OR and the other one AND. And I want you to find a connectivity pattern, so weights that connect node 0 with node 0 here and node 0 with node 1 here, so that node 0 becomes the OR function, so that we get the result of this truth table, and the second node here should behave as the AND function. Yeah, that's the exercise. Have fun.